Welcome to this coding walkthrough. In this session, we'll tackle problem number 29, divide two integers. We'll explore the problem statement, break it down into manageable steps, and discuss an intuitive approach to solve it. Let's get started. In this problem, you are tasked with dividing two integers, dividend and divisor, but without using the standard multiplication, division, or modulus operators. Your goal is to calculate the quotient resulting from this division. The quotient should be truncated towards 0, meaning any fractional part is dropped. For instance, if the result is 8.345, it should become 8, and if it's minus 2.7335, it should become minus 2. Additionally, you need to consider the constraints of a 32-bit sign integer range, which is from minus 2 to the power of 31 to 2 to the power of 31 minus 1. If the calculated quotient exceeds this range, you must clamp it to these bounds. For example, if the quotient is larger than 2 to the power of 31 minus 1, you return 2 to the power of 31 minus 1, and if it is smaller than minus 2 to the power of 31, you return minus 2 to the power of 31. The input consists of two integers, dividend, which is the number to be divided, and divisor, the number by which you divide. The output for this problem is a single integer, representing the truncated quotient of the division. Let's take an example to clarify this further. Suppose the dividend is 10 and the divisor is 3. When you divide 10 by 3, the result is 3.333. Since we truncate the fractional part, the output becomes 3. This is the integer result of dividing 10 by 3, with truncation towards 0 applied. Now, consider another example where the dividend is 7 and the divisor is minus 3. Dividing 7 by minus 3 gives minus 2.333. Again, truncating towards 0 means we drop the fractional part, so the result becomes minus 2. This behavior ensures that the quotient is always an integer value, with any decimal portion removed. Another interesting case arises when the dividend is -2147483648, which is the smallest 32-bit signed integer, and the divisor is minus 1. The division of -2147483648 by minus 1 would result in 214,748,3648. However, this value exceeds the maximum limit of a 32-bit signed integer, which is 2 to the power of 31 minus 1 or 214,748,3647. To handle this, the result is clamped to 214,748,3647. This ensures that the output adheres to the constraints of a 32-bit signed integer. As you work through this problem, keep in mind edge cases, such as when the divisor is 1 or minus 1, when the dividend is 0, or when the result exceeds the valid range. These scenarios require careful handling to produce the correct output. To solve the problem of dividing two integers without using multiplication, division, or mod operators, we first consider the brute force approach. This method involves repeatedly subtracting the divisor from the dividend, counting how many times this subtraction can be done before the remainder becomes less than the divisor. For example, dividing 10 by 3 would require subtracting 3 from 10 until we are left with a remainder less than 3, which gives a quotient of 3. While this approach is simple and intuitive, it is highly inefficient for large numbers. The time complexity, quotient, scales linearly with the magnitude of the result. So, for a case like dividing 10 to the power of 8 by 1, it would take 10 to the power of 8 iterations, making it impractical for solving problems with large inputs. To overcome this inefficiency, we need a more optimized solution. The optimized approach leverages bit manipulation and the idea of exponential growth to enhance efficiency. Instead of subtracting the divisor one unit at a time, we subtract exponentially increasing multiples of the divisor. This is achieved by doubling the divisor repeatedly, using left shift operations, and subtracting the largest multiple that fits within the dividend. For instance, when dividing 10 by 3, we first double the divisor to 6, which fits within 10. After subtracting 6, we are left with 4, and we repeat the process with the remainder. The use of bitwise shifts makes this approach computationally efficient, with a time complexity of log dividend. This method not only speeds up the process significantly but also adheres to the problem constraints of avoiding multiplication and division. However, there are challenges to address, such as handling special cases like overflow and ensuring the result remains within the valid 32-bit signed integer range. Given these considerations, the optimized approach using bit manipulation is the best strategy for solving this problem. Its logarithmic time complexity makes it highly scalable and efficient for large inputs. Furthermore, it works for both positive and negative numbers by determining the results sign based on the dividend and divisor and applying the same logic to their absolute values. The steps for this strategy include handling edge cases like division by zero or overflow, determining the sign of the result, and working with absolute values to simplify the calculations. The heart of the method involves repeatedly subtracting the largest possible multiple of the divisor from the dividend using bit manipulation. Finally, the result is clamped to ensure it fits within the 32-bit signed integer range. While this approach is more complex to implement than the brute force method, the trade-off is justified by the significant performance improvement. The chosen approach balances performance and adherence to the problem's constraints. The logarithmic time complexity makes it suitable for handling large inputs, and by using only addition, subtraction, and bitwise operations, it complies with the requirement to avoid multiplication and division. While it requires careful handling of edge cases such as overflow and sign determination, the solution is robust and efficient. This makes it a clear choice over the brute force method, which is simpler but impractical for large inputs due to its linear time complexity. Overall, the optimized solution offers the right combination of efficiency, scalability, and compliance needed to solve this problem effectively. To solve this problem, we need to implement integer division without using the multiplication, division, or modulo operators. The goal is to compute the quotient when we divide a given dividend by a divisor, ensuring the result truncates toward zero. First, we initialize by taking the absolute values of both the dividend and divisor to handle any negative numbers uniformly. We also establish a variable called quotient to store the result, which starts at 0. Additionally, we record the signs of the original inputs so we can adjust the final result accordingly. Next, we use a repeated subtraction approach. As long as the dividend is greater than or equal to the divisor, we subtract the divisor from the dividend and increment the quotient with each operation. Once this loop completes, we determine the final sign of the quotient. If the dividend and divisor initially had opposite signs, we make the quotient negative. This step ensures that the sign of the result is accurate according to the rules of division. Now, let's consider edge cases and the efficiency of this approach. First, if the divisor is 0, we need to handle this explicitly because division by 0 is undefined. Similarly, if the dividend is 0, the result is simply 0. Another important edge case is when the result exceeds the 32-bit signed integer range, which is from -2 to the power of 31 to 2 to the power of 31 . These overflow scenarios must be addressed to ensure correctness. In terms of efficiency, the brute force approach has a time complexity of O(n), where n represents the quotient. This is because we repeatedly subtract the divisor from the dividend, which can take many iterations for larger inputs. By working with absolute values, the comparison and subtraction operations are simplified, leaving the sign adjustment for the end. It's also important to handle special cases like when the dividend is -2 to the power of 31 and the divisor is -1, as this results in an overflow scenario. This approach uses simple data structures to keep the implementation efficient. The main variables include the dividend and divisor, which are converted to their absolute values during computation, and the quotient variable that incrementally stores the result. The method relies solely on these variables, ensuring a space complexity of O(1). Let's walk through an example to see this in action. Consider a dividend of 10 and a divisor of 3. First, we take their absolute values, so dividend remains 10 and divisor remains 3. We initialize the quotient as 0. Then, we repeatedly subtract the divisor from the dividend. In the first iteration, 10 minus 3 equals 7, and we increment the quotient to 1. In the second iteration, 7 minus 3 equals 4, and the quotient becomes 2. In the third iteration, 4 minus 3 equals 1, and the quotient becomes 3. At this point, the dividend is less than the divisor, so we stop. Since both inputs were positive, no sign adjustment is needed. The final result is a quotient of 3. To optimize this approach, we can implement a few enhancements. First, we can include an early exit condition. If the dividend is initially smaller than the divisor, we can immediately return 0 without performing any further calculations. A more significant optimization involves using bit manipulation. Instead of subtracting the divisor repeatedly, we can double the divisor and subtract larger chunks from the dividend. This approach reduces the number of iterations drastically, achieving a time complexity of O log n. While the brute force method is a good foundational approach, these optimizations make the algorithm much more efficient, especially for larger inputs. By subtracting larger chunks or exiting early when possible, we retain accuracy while improving performance significantly. Here, we start with a Python implementation for dividing two integers without using the division operator. First, we define constants for the 32-bit integer limits, which are important because the result must stay within this range. Next, we handle a specific edge case. When the dividend is the minimum 32-bit integer value and the divisor is -1, the result would mathematically exceed the maximum limit. To prevent overflow, we directly return the maximum integer value in this scenario. Now, we determine the sign of the result by checking if the dividend and divisor have opposite signs. If they do, the result will be negative. For simplicity, we convert both the dividend and divisor to their absolute values, as the sign will be applied at the end. The division itself is implemented using bit manipulation. We initialize the quotient to 0 and repeatedly subtract the largest possible shifted divisor from the dividend. For each subtraction, we calculate how many times the divisor can be shifted left, doubling it each time, until it exceeds the dividend. Once we find the largest valid shifted divisor, we subtract it from the dividend and update the quotient accordingly by adding the corresponding power of 2. After calculating the quotient using bit manipulation, we now apply the sign to the result. If the initial sign was determined to be negative, we negate the quotient. Finally, we ensure that the result is clamped within the valid 32-bit sign integer range. This step guarantees that the quotient does not exceed the maximum or fall below the minimum allowed values. To achieve this, we return the quotient after using the max and min functions to bound it between the int_min and int_max constants. This concludes our Python implementation for dividing two integers while adhering to all the problem constraints. In this Java implementation, we start by defining the solution class and the divide method. The method is designed to handle the division of two integers without using multiplication, division, or modulus operators. To ensure we stay within the limits of 32-bit integers, we define constants for the maximum and minimum integer values, int_max and int_min. An edge case is addressed early. If the dividend is the smallest possible integer value, int_min, and the divisor is -1, the result would exceed the maximum positive value for a 32-bit integer. In this case, we simply return int_max to prevent overflow. Next, we determine the sign of the result by checking if the dividend and divisor have opposite signs. If they do, the result will be negative. For the calculation itself, we convert both numbers to their absolute values and cast them to long data types to avoid issues with integer overflow during intermediate operations. Using bit manipulation, we then initialize the quotient to 0 and begin a loop that performs the division. The loop continues as long as the absolute value of the dividend is greater than or equal to the absolute value of the divisor. Inside the loop, we prepare to find the largest multiple of the divisor that fits into the dividend by starting with the divisor and progressively doubling it. The doubling of the divisor is achieved using the left shift operator, which effectively multiplies the current divisor by 2 at each step. We also maintain a counter, number shifts, to track how many times the divisor has been doubled. This process stops when the doubled divisor exceeds the current value of the dividend. At that point, we subtract the largest shifted divisor from the dividend and increment the quotient by the corresponding power of 2, represented as 1 left shifted by number shifts. This ensures we account for how many multiples of the divisor fit into the dividend. Once the loop completes and the full quotient has been calculated in its absolute form, we apply the appropriate sign to the result based on the earlier determination of whether the result should be negative. Finally, we ensure the result remains within the valid range for 32-bit sign integers. To do this, we use the math.max and math.min functions to clamp the quotient between int_min and int_max. The method then returns the safely calculated result. Here, we start with the problem of dividing 10 by 3. First, we set up the inputs. The dividend is 10 and the divisor is 3. We define constants for the 32-bit integer range, where int_max is 2 to the power of 31 1 and int_min is minus 2 to the power of 31. Since both the dividend and divisor are positive, the result will also be positive, so we set the negative flag to false. Next, we convert both numbers to their absolute values, which in this case remain the same. We also initialize the quotient to 0. Now, we begin the first iteration of the outer loop. Since the dividend, which is 10, is greater than or equal to the divisor, which is 3, we proceed. Inside the inner loop, we start with the divisor as the current divisor, which is initialized to 3, and the shift count, number_shifts, is set to 0. Doubling the current divisor gives us 6, and we increment number_shifts to 1. We stop doubling since doubling it again would exceed the dividend. Back in the outer loop, we subtract the current divisor, which is 6, from the dividend, reducing it to 4. We then add 1 shifted left by number_shifts, which is 2, to the quotient, making the quotient now equal to 2. Next, we proceed to the second iteration. The dividend is now 4, which is still greater than or equal to the divisor, 3, so we continue. Again, we start the inner loop with the current divisor set to 3, and number_shifts initialized to 0. This time, we don't double the current divisor because doubling it would exceed the dividend. Exiting the inner loop, we subtract the current divisor, 3, from the dividend, leaving a remainder of 1. We then add 1 left shifted by number_shifts, which is 1, to the quotient, updating the quotient to 3. Now that the dividend is less than the divisor, we exit the outer loop. In the final step, we check the sign of the result. Since the negative flag is false, the quotient remains positive. We ensure the quotient is within the 32-bit integer range, which it is, so the final result is 3. Now, let's look at the example of dividing -7 by -3. First, we set up the inputs. The dividend is -7, and the divisor is -3. We use the same constants for the 32-bit range, int_max and int_min. Since both the dividend and divisor are negative, their signs cancel out, making the result positive, so the negative flag is set to false. We convert both numbers to their absolute values, resulting in a dividend of 7 and a divisor of 3. The quotient is initialized to 0. For the first iteration, the dividend, which is 7, is greater than or equal to the divisor, 3, so we proceed. Inside the inner loop, the current divisor starts as 3, and number_shifts is 0. Since doubling the current divisor would exceed the dividend, we exit the inner loop. We then subtract the current divisor, 3, from the dividend, reducing it to 4. Adding 1 left shifted by number_shifts, which is 1, to the quotient updates the quotient to 1. In the second iteration, the dividend is now 4, which is still greater than or equal to the divisor, 3. Again, we enter the inner loop with the current divisor set to 3 and number_shifts initialized to 0. As before, doubling the current divisor would exceed the dividend, so we exit the inner loop. We subtract the current divisor, 3, from the dividend, leaving 1. Adding 1 left shifted by number_shifts, which is 1, to the quotient updates it to 2. Since the dividend is now less than the divisor, we exit the outer loop. Finally, we adjust the sign of the result based on the negative flag. Since the flag is false, the quotient remains positive. We ensure the result is within the 32-bit range, and the final output is 2. For the third example, we divide -2147483648 by 1. The dividend is -2147483648, and the divisor is 1. We define the same constants for the 32-bit integer range. Since the dividend is negative and the divisor is positive, the result will be negative, so we set the negative flag to true. Converting both numbers to their absolute values gives a dividend of 214,748,3648 and a divisor of 1. The quotient is initialized to 0. Now, we enter the outer loop, where we repeatedly subtract the divisor, 1, from the dividend. Each time we subtract 1, we increment the quotient by 1. This process continues for 214, 748, 3648 iterations until the dividend is reduced to 0 and the quotient becomes 214, 748, 3648. In the final step, we apply the sign to the quotient. Since the negative flag is true, the quotient is made negative, resulting in -21474833648. We ensure the result lies within the 32-bit range, which it does, so the output is -21474833648. The time complexity of the solution can be understood by analyzing the two loops involved. First, the outer while loop continues executing as long as the dividend is greater than or equal to the divisor. In each iteration, the algorithm reduces the dividend by the largest shifted value of the divisor, which is determined using the inner loop. Since the dividend is reduced exponentially due to the doubling effect of bit shifts, the number of iterations in this loop is proportional to the logarithm of the dividend, specifically log dividend, in base 2. Next, the inner while loop determines the largest multiple of the divisor that fits within the current dividend. This involves doubling the current divisor repeatedly, which also happens logarithmically with respect to the dividend. However, since the inner loop completes its work within each iteration of the outer loop, it does not significantly change the overall time complexity. As a result, the total time complexity is dominated by the outer loop and is O log dividend. The overall time complexity, therefore, consolidates to O log dividend, with the outer loop being the primary contributor. The inner loop, while also logarithmic, is nested within the outer loop and completes its operations per iteration of the outer loop, so it does not alter the dominant time complexity. Moving on to space complexity, the solution is highly efficient with a space complexity of O1. This is because the algorithm uses only a fixed set of variables, such as int_max, int_min, negative, quotient, current_divisor, and number_shifts. These variables require constant space regardless of the size of the inputs. Importantly, no recursion is involved, and the algorithm does not rely on dynamically allocated data structures like arrays or lists. All calculations are performed directly on these fixed variables, ensuring that memory usage remains constant and does not scale with the size of the inputs. Since the space required is independent of the size of the dividend and divisor, the space complexity remains O1. Comparing this optimized approach to a naive method helps illustrate its efficiency. A naive approach would involve repeatedly subtracting the divisor from the dividend until the dividend becomes smaller than the divisor. This would result in a time complexity of O dividend/divisor, as each subtraction reduces the dividend by the value of the divisor. For large inputs, this approach becomes extremely inefficient. In contrast, the optimized solution uses bit manipulation, specifically left shifts, to subtract large multiples of the divisor in each iteration. This reduces the number of iterations to O log dividend, making it significantly faster and far more scalable for large inputs. This comparison highlights the advantage of using an approach based on logarithmic reduction rather than linear subtraction. To summarize, the optimized solution achieves a time complexity of O log dividend, in all cases best, average, and worst. Even in the best case, the algorithm must iterate logarithmically due to the exponential reduction of the dividend. For typical inputs, the behavior remains consistent, and in the worst case, the logarithmic nature of the reduction ensures that the algorithm remains efficient. Mathematically, this is supported by the fact that the outer loop continues until the dividend is less than the divisor, and each iteration reduces the dividend by a value proportional to a power of 2. This exponential decrement means the number of iterations is directly proportional to the logarithm, base 2, of the dividend. The inner loop, which performs left shifts to determine the largest multiple of the divisor, also runs logarithmically but contributes only a constant factor per iteration of the outer loop. This solidifies the overall time complexity as O log dividend. The space complexity, as stated earlier, remains O1, since no additional memory is required beyond the fixed set of variables. When working on the divide two integers problem, there are a few common mistakes to watch out for. First, some developers mistakenly use addition instead of subtraction in their brute force implementation. For example, instead of reducing the dividend by the divisor, they accidentally add the divisor, which completely changes the logic of the operation and leads to incorrect results. Another issue is infinite loops when handling edge cases. If the dividend is smaller than the divisor, like 3 divided by 10, and there's no proper stop condition, the loop may never terminate. To avoid this, you should explicitly check if the dividend is less than the divisor and exit early. Lastly, negative numbers can easily trip people up. For instance, if you're dividing -10 by 3, the answer should be -3. Failing to properly account for the sign of the inputs and the resulting quotient is a common source of bugs. To fix this, track the signs of the dividend and divisor separately, and adjust the sign of the quotient at the end of the computation. Another critical challenge arises with integer overflow in edge cases. Specifically, if the dividend is the smallest possible 32-bit signed integer, like -2 to the 31st power, and the divisor is -1, the result would exceed the range of a 32-bit integer. To handle this, you should implement a check for this specific case and return the maximum 32-bit signed integer value, which is 2 to the 31st power -1. Additionally, relying on a brute force approach for all cases is highly inefficient, especially with larger numbers. While brute force might work for small inputs, it becomes computationally expensive as the numbers grow. An optimized method, like binary search or bit manipulation, should be used to handle larger inputs more efficiently. In interviews, it's important to demonstrate your ability to handle edge cases. Common scenarios include division by 0, negative numbers, and integer overflow. Showing that you've thought through these situations is crucial. Beyond that, interviewers often look for your ability to optimize. While brute force is a good starting point to show problem understanding, you should quickly transition to more efficient approaches such as binary search or bit manipulation. Also, make sure you discuss time complexity. For example, brute force has a time complexity of O(n), while optimized methods can achieve O log n. Highlighting these trade-offs shows your awareness of efficiency. Finally, be meticulous when handling the signs of the dividend and divisor. This is a frequent source of bugs, so having a clear, methodical approach will make a strong impression. Related problems can provide great practice and deeper insight into similar concepts. For example, LeetCode 371, sum of two integers, involves performing arithmetic without using standard operators, making it an excellent warm-up for bit manipulation. Another related problem is LeetCode 343, integer break, which focuses on breaking integers into parts while optimizing the product, often requiring efficient division and multiplication strategies. On the topic of alternative approaches, binary search is one powerful method. Here, you start with a range, typically from 0 to the dividend, and narrow it down by checking if the midpoint times the divisor is greater or less than the dividend. This approach has a time complexity of O log n, but requires careful handling of boundary conditions and additional variables. Bit manipulation is another efficient approach, where you use bitwise shifts to repeatedly double the divisor and subtract from the dividend. While it's highly efficient, also with O log n complexity, it's harder to implement and debug, especially when dealing with signs. Finally, there's the brute force method, which involves repeatedly subtracting the divisor from the dividend until the dividend is reduced to 0 or less. While this method is straightforward and easy to implement, it has a time complexity of O(n), making it highly inefficient for larger inputs. This inefficiency makes it less suitable for problems with strict performance requirements, but it can still serve as a simple starting point to develop and understand the basic logic of the problem before moving on to more optimized solutions. Great job making it to the end. Today, we covered problem number 29, divide two integers, and discussed a simple brute force approach to solve it. Remember to practice identifying edge cases and optimizing solutions. Thank you for watching, and we'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!